Alright, some facts about the definite integral. First of all, typically we assume that the lower limit is less than the upper limit. There's really nothing wrong though with the lower limit being bigger than the upper limit. So that just feels a little weird though, because we're usually used to the lower limit being smaller. Just what it is, sort of convention. So in any case, if it makes you feel better, you can always swap the limits of integration. But if you do so, you pay a small price. You have to put a minus in front of the integral. If you integrate from a to a, you're integrating over an interval of length 0. The area under a curve over an interval of length 0 is 0. So the interval is 0. If you're integrating a constant from a to b, well, it's pretty much just a rectangle, and you get c times b minus a. B minus a is the length of the base of the rectangle. C is its height. Although if c is negative, we count the area negative, and it ends up being negative. Great. The integral from a to b of f of x plus or minus g of x is the integral from a to b of f of x plus or minus the integral of a to b from a to b of g of x. So the integral of the sum or difference is the sum or difference of the integrals. Great. If I have a constant multiple of a function, I can pull the constant out. Great. So the integral of the constant multiple is the constant multiple of the integral. And finally, this is useful for sort of breaking up integrals into pieces where we can more easily deal with it. The integral from a to b of f of x plus the integral from b to c of f of x, notice this upper limit equals this lower limit, is the same thing as integrating from a to c, f of x d of x. So if we go from a to b and then b to c and add them together, it's the same as just going from a to c. So let's apply some of this stuff. Let's let f of x be the piecewise defined function, which is 3 minus 2 root 1 minus x squared for x between 0 and 1, and equal to 3x when x is greater than or equal to 1. Let's evaluate the integral of f from 0 to 2. So first of all, this function has one definition on half of this interval from 0 to 1, and another definition on the other half from 1 to 2. So the first thing we're going to need to do is split this integral up into two pieces. The integral from 0 to 1 and the integral from 1 to 2. From 0 to 1, we'll replace the function with its definition on that interval. For the other interval, we'll replace the function with its definition on that interval. So we have the integral from 0 to 1 of 3 minus 2 root 1 minus x squared plus the integral from 1 to 2 of 3x. Now I will use some facts. The integral of a difference is the difference of the integrals. So I can break this up into the integral from 0 to 1 of 3 and the integral from 0 to 1 of 2 root 1 minus x squared, and I'm subtracting them. But also I can pull out constant multiples. So I pull out the 2 here, and I'm just left with 2 times the integral from 0 to 1 of the square root of 1 minus x squared dx. And we've already evaluated that before, earlier today. And I'm going to add to that integral from 0 to 2 of 3x dx. I don't really need to do this, but I might as well. I'll pull out the constant multiple of 3, so I just have the integral from 1 to 2 of x dx. What is that equal to? Well, geometric considerations allow us to compute it. I've just graphed a little graph over here of the function y equal to x. I'm looking between 1 and 2. I get this trapezoidal shape, and it's not too difficult to show that its area is equal to 3 halves. So, the integral from 0 to 1 of 3 is 3 times the difference of the limits according to one of our properties of integration. The integral from 0 to 1 of root 1 minus x squared is pi over 4 from geometric considerations as we saw before. So I have 3 times 1 minus 2 times pi over 4 plus 3 times this area, which is 3 halves. I combine it all and I get 15 halves minus pi over 2. So here's question 1. Using whatever we have worked with so far, geometry, these basic rules of integration, let's evaluate the integral from negative 2 to 0 of 3 times the square root of 4 minus x squared, that's a semicircle, plus 2x minus 3 dx. Okay, so the last thing I'd like to talk about are some comparison facts about integrals, I suppose some inequalities. So first, if we have a function f of x which is non-negative, its integral has to be non-negative. The idea here really is this. If f of x is greater than or equal to 0, then its graph lies above the x-axis. So if you compute the area between f of x and the x-axis, the integral should evaluate it positively, as we've spoken about, and the area is an area. It can't be counted negative. It's above the x-axis, so this has to be positive. Similarly, if f of x is greater than or equal to g of x, then the integral from a to b of f of x is greater than or equal to the integral from a to b of g of x. And this fact pretty much follows from this fact and the fact that the integral of a difference is the difference of the integrals. Both of these are just useful things to use sometimes. They're useful. This is useful for interpreting answers sometimes, making sure you're right. A very basic check is I've got a positive function, I evaluated its integral, I got a negative number, I did something wrong. This here is could be a good way of estimating some integrals. Finally, if we know that a function f of x is bounded between a small number m and a big number, big M, so a minimum and a maximum, then the integral itself is bounded between multiples of these numbers. Specifically, the integral is at least the minimum times the length of the interval we're integrating over, and it's at most the maximum value times the length of the interval we're integrating over. So really, we should be thinking of these as the sizes of some rectangles, and this is just saying that this integral is bigger than this minimizing rectangle, but smaller than this maximizing rectangle. Alright, so just one more example. We're going to bound the integral from 1 to 2 of 1 over x dx using some of these facts. First of all, 1 over x is greater than or equal to 1/2 for all values of x between 1 and 2. 1 over x is a decreasing function. The smallest it is on this interval is 1/2, so it's always bigger than 1/2 on this interval. So the integral from 1 to 2 of 1 over x dx is greater than or equal to 1/2, which is this minimizing value, times the length of the interval, which is 2 minus 1. So we just get 1/2. Okay, so this integral is greater than 1/2. However, 1 over x is less than or equal to 3/2 minus 1/2 x. Where did I pull this out of? Well, this is actually the secant line of this curve, y equal to 1 over x, from x equal to 1 to x equal to 2. Now, the thing about this function, 1 over x, is that it's concave up, and that actually implies that the secant line will always lie over the function. So the secant line is bigger than the actual function, and so the integral from 1 to 2 of the secant line is bigger than the integral from 1 to 2 of 1 over x. And you can use some geometric considerations to find that the integral of the secant line is 3/4. It's a trapezoid of base 1, height 1 on one side, and height 1/2 on the other side. So the trapezoid area formula gives us 3/4. So this integral from 1 to 2 of 1 over x dx is at least 1/2, but it's less than 3/4. Okay.